Okay, my name is Netanel Ratner, and I'm the chief technologist of the computer vision at Rafael. Rafael does not usually need an extensive introduction. Nevertheless, Rafael is a government-owned defense industry. Our primary goal is to contribute to the defense and security of the State of Israel. And we do that in more than one manner. The first way is well known, so we deal with developing state-of-the-art defense systems for the Israeli Defense Forces. Some of you are maybe familiar with our Iron Dome missile interceptance system, maybe the Trophy tank defense system, and other classified systems. The other ways we contribute to the security of Israel are economical. So we are the largest employer in the north, in the Galilee, and as a profitable company, we also pay our taxes and yields our dividends to the government of Israel. The computer vision research and development team at Rafael consists about 160 research engineers. Most of them have master's and PhD degrees. And I think we cover almost the entire set of so-called classic computer vision problems, starting object detection and tracking, image registration, 3D reconstruction, and so on and so forth. Being a research group, we try and keep a close look about recent progress and innovations in the academia. But due to the specific nature of military applications, we need to be extremely cautious and very selective about the technologies that we choose to integrate within our systems. So here I've enumerated 4 typecastes of military systems, and the different categories are distinct by the similarity between military systems and their equivalent civilian systems. So we can look at intelligence systems, and by and large, there is no major difference between a civilian intelligence system and a military intelligence system. They are quite the same. Namely, for example, one can construct a civilian intelligence system that monitors communications in a social network, trying to profile someone for its consumption preferences, for advertising purposes. And the equivalent military systems would be a system that monitors the same social network and the same communications, but trying to profile someone for the risk of that particular someone to take part in terrorist acts. And by and large, since the nature of these applications is quite the same, the flow of technologies between the civilian world and the military world is relatively free. And much like intelligence systems, there are the surveillance systems that are pretty much close to one another, the military variant and the civilian variant. So again, there is no great difference in constructing a surveillance camera that is designed to alert for shoplifting in a shopping mall versus a military or homeland security surveillance camera that is designed to alert for any criminal or terrorist behavior in a public area. So these are quite the same. And as for the next 2 categories, the differences are a bit more significant between the military variants of the system and the civilian variants. Namely, for example, in autonomous driving, there are some major differences, and also with drone navigation. And as for the last category, autonomous weapons, I don't think there is an equivalent civilian system. So we're being here very selective about the technologies we wish to adopt in autonomous weapons. So let's elaborate a little bit about the differences in autonomous driving, civilian autonomous driving versus military autonomous driving. I think the major difference lies in the fact that the variety of scenarios for military autonomous driving is even greater than in civilian, so-called conventional urban driving, especially relating to off-road scenarios, which again can be very diverse and very interesting. So I'll show you a little illustration. Have some difficulties activating the hyperlinks here. כן, תודה. אוקיי, אתה יכול להפעיל אותו? Okay, thank you. So here we can see an illustration of obstacle avoidance and semantic segmentation for military autonomous driving. The thing is that since the variety of the scenarios, again, is enormous, and the amount of data that we have is limited, we cannot adopt an end-to-end methodology in tackling the autonomous driving. So namely, we do not employ a unified network that takes as an input the live imagery from the cameras and then produces as an output the steering commands. Rather than that, what we wish to do is we construct a multiple stage system that is built from distinct individual building blocks. Some of them are based on deep learning methods, and some of them are based on even legacy algorithms. For example, in this illustration, what you can see is a semantic segmentation that is essentially a deep learning based system, but it relies on a very traditional, very legacy algorithm of 3D reconstruction. Could you help me with the movie, please? The video clip? Okay, so here you can see semantic segmentation results. You can see that the algorithm distinguishes between the drivable regions and the obstacle, the vegetation. There are all kinds of obstacles, and obviously for more realistic scenarios, this is even more difficult. Could you go back, please? Are you helping me with the mouse? So please go back to the previous slide. לא, הקודם. הקודם. Yeah. Okay. Sorry for that. I should have known better. Anyway, the next challenge that we typically tackle is that the other players in our scenarios are not always innocent. So in civilian autonomous driving, one can assume that pedestrians or other human figures, as well as other cars, are by and large cooperative with the original task of transporting someone safely from one point to the other point. I think this assumption is no longer valid when we move to military autonomous driving. Could you please hit the hyperlink? Yeah, the second one. So what we need to do is we need to integrate into our systems all kinds of algorithms that can identify malicious or, let's say, unproductive behaviors on behalf from the other participants in a scenario. So we typically use LSTM-based systems to try and identify dangerous behaviors or counterproductive behaviors. And also, we rely on networks that are freely available in the academia and in open source for identifying human figures, but we augment these networks with algorithms that are designed to distinguish armed people from unarmed people, and we can see here a sample of the results. Please hit the back button. Thank you. And the third issue that we typically encounter is the issue of what we call battlefield-related clutter. So for state-of-the-art autonomous driving systems, there is typically some additional information about the surrounding of the vehicle, for example, a model of the structures nearby the vehicle. The thing is that during wartime, this model tends to change quite rapidly in a short period of time. As you can see here, I think this illustration is from Gaza. So you cannot trust with 100% or 100% certainty the fidelity of the structure model like you do in other systems. The appearance of buildings changes quite rapidly during wartime. And there are also fires erupting here and there, and fires for an infrared imager are quite destructive, as you can see on the right-hand side here. Please go back. Okay. We'll talk maybe later on about GPS jamming if we have some time. And a totally different challenge is for a pack of autonomous vehicles to perform collaboratively a common task. So this is a challenge of its own. The next category of products I don't think have any equivalent in the civilian world. So these are autonomous weapons. Smart weapons or smart bombs has been around ever since the 70s, but there is a great distinction between smart bombs and smart bombs. They can autonomously navigate to a designated target. The thing is that the operator needs to specifically designate the target of choice, either by laser illumination or feeding in the coordinates of the targets. For autonomous weapons, we need to have the weapon itself, we need to let the weapon itself decide what is the correct target out of a selection of targets, and I think mistakes here are fatal. So we need to take extreme caution with these kind of algorithms. I think the most severe challenge that we have is the quality of imaging systems and the quality of images. As you can see, we have here an image taken by a seeker head of a bomb. This is an infrared image. As you probably speculate, bombs are disposable products, so the imager shouldn't be very expensive. So we use inexpensive, uncooled thermal imaging systems. And I think it is a bit difficult even for the naked eye or the human being to distinguish here the target from other constructions in the imaged scene, let alone the algorithm. So this is a severe challenge that we encounter. Could you please hit the first hyperlink? Thank you. Here is yet another illustration. This is a system designed to track down drones that may pose a threat. I don't know if you've heard recently about the incidents in the Heathrow airport. So this is a system that is designed to neutralize such a threat, and you can see that the quality of the images is relatively low and the size of the targets is relatively small, which poses a very serious challenge for our systems. Please go back. Okay, our next challenge, and I think I'm running out of time here, but our next challenge is the data itself. So unlike images of cats or human figures or dogs that are freely available in the internet, our potential targets might be very exotic in the sense that no real data, it's either that we have very little data about the target or there's no data whatsoever. So we need to employ methods that are relatively well known. Could you hit the second hyperlink, please? Okay. So one of our ways to overcome the lack of data is by using domain adaptation. So we use networks that are trained on visual range wavelengths for infrared imagery, and then we add in some infrared images to the training procedure. and somewhat adapt the original network to cope with infrared images. So this is one strategy. Another strategy for producing data is using synthetic data. So we've constructed an electro-optic simulator that takes into account almost the entire set of physical effects that we know of, both from the target and the atmosphere in the imaging system, and it synthesizes infrared images that look almost real. The thing is that almost real doesn't count for training a deep learning-based algorithm, so we need to make the images themselves as real as possible. So the strategies that we take for that matter is to take the original synthetic images produced by the electro-optic simulator and further modify them using GAN, using generative adversarial network, and techniques taken from style transfer. So we further modify the images using style transfer techniques to create images that are as close as possible to realistic images, so that we can train our deep learning methods to distinguish between targets and other objects. So here you can see an illustration. And the third strategies that we currently consider is meta-learning. So we try to evolve. This is an emergent strategy. This is relatively new in the literature, but what we try to do is we try to evolve the architectures of our deep networks to have the same state-of-the-art results, but with smaller and smaller quantities of data. So this looks promising, but there are no real results yet. Could you go back to the original slide? Thank you. The other significant challenges that we encounter, again, are battlefield-related clutter, as you've seen in the case of the autonomous driving. So fires, bombs, smoke, they all interfere with the algorithms, and we need to overcome such effects and artifacts. GPS jamming, so I don't know if you're familiar with the problem, but it's pretty easy nowadays to jam a GPS, and then the autonomous bomb wouldn't know its location. This is quite dangerous, so what we do to cope with this challenge, could you hit the hyperlink, please? GPS jamming. No, not this one. The third one, thank you. So what we do is we use a relatively old technique. So we have a photogrammetric infrastructure fed into our bombs, and then the photogrammetric infrastructure is compared to the live imagery taken from the seeker head of the bomb, so we can estimate our location without any use of a GPS system. Could you go back, please? Okay, and there are all kinds of other challenges that we handle on a daily basis. Apart from the purely technical challenges that I've presented so far, there are all kinds of other challenges. For example, for security reasons, we're not connected to the internet. This poses a great challenge nowadays, so trying to have everything on-prem without any connection whatsoever to the World Wide Web is almost impossible to work with, but we somehow manage to cope with it. There are all kinds of regulatory constraints and license issues that we need to handle when working with open source code, but we have a pretty active and vigorous legal department as well, so we can overcome this challenge as well. There are all kinds of ethics issues, and I think that's worth a talk of its own, because the implication of an algorithm making decisions that can cost human lives are pretty significant. So I won't get into the ethics problems right now, but this is something that we constantly consider. And of course, the competitive market, Rafael as being a government-owned industry, subject to all kinds of regulatory constraints with respect to the compensation, but we try to overcome this problem as well. And in spite of all the challenges, we try to play an open game as we can, and we encourage all other industries and defense bodies to play as open as possible. And I think an excellent example for playing open would be MAFAT. MAFAT is a part of the Ministry of Defense. MAFAT's classification challenge, I urge you all to look at the web and look at the classification challenge published by MAFAT. And to sum everything up, it's our people that makes the difference and contribute to the security of Israel. Thank you.